Great. So it is a great privilege for me to introduce our Millward Colloquium speaker, Dr. Nicholas Christakis, who will be sharing some of his research with us today on social networks. So one of the things that makes social network analysis so fun and so interesting is that the techniques really cut across disciplinary boundaries, with a variety of applications in public health, in medicine, sociology, psychology, and so on. And Dr. Christakis' work spans all of these disciplines in a really deep way. He first got his MPH from the Harvard School of Public Health, then his MD from Harvard Medical School, and then just for kicks, his PhD in sociology from the University of Pennsylvania. And he's now appointed in no fewer than 5 departments at Yale University. So if you take a look at Dr. Christakis' long list of publications, it's easy to appreciate the truly interdisciplinary nature of his research and the intellectual contributions that he regularly makes in several fields with little regard for disciplinary boundaries. So it's customary for these kinds of introductions to list the speaker's academic accolades and achievements. But if I were to start now, we'd reach the end of the allotted time without ever hearing him say a single word. So I'm going to stick with some of the highlights. He's an elected member of the National Academy of Medicine, the American Association for the Advancement of Science, and the American Academy of Arts and Sciences. He has authored over 200 scientific articles and several popular science books. And as of last night, Google Scholar says that he's been cited 58,455 times. He was once named one of Time Magazine's 100 most influential people in the world, twice named by Foreign Policy magazine as one of the world's top 100 thinkers. And if I keep going, Dr. Christakis really isn't going to have any time to speak. So in normal times, this is where I would ask you to join me in welcoming him to our Colloquium series, but Zoom applause is inevitably really awkward. So I'm gonna try asking you to do something a little less awkward, which is to think really hard about clapping. And I hope Dr. Christakis is now able to telepathically feel all of the warm welcome that we're collectively thinking. And Dr. Christakis, the floor is now yours.
Well, thank you so much for that very kind introduction, and thank you all for having me. And I wish I could be there in person when I think I was approached about this a year ago or something, and I was delighted to accept, and I was especially flattered that the graduate students had somehow thought I might have something useful to say, and so I was looking forward to coming to see you, and I'm sorry we're doing it under these circumstances. As an aside, my wife and I recently adopted a 10-year-old son. My other children are in their 20s, and so we, for a variety of reasons, have decided to raise this boy in Vermont, and so I'm speaking to you now from Vermont, where I have been in lockdown since March. And part of my response to that was to try to find useful things to do. And I just finished a book called Apollo's Arrow, the profound and enduring impact of coronavirus on the way we live. That book is coming out October 27th. And so I spend the first 4 months of lockdown every day writing that book. So if you want, during the QA, I'm also happy to digress and talk a little bit about some applications of some of the stuff that I'm discussing with you today on how pathogens spread, and more pertinently, how human responses to pathogens spread, because you can think of the epidemic as a dueling contagion of a biological contagion that's spreading across network ties and a social contagion of behaviors, whether it's mask wearing or vaccine adoption or vaccine avoidance. And the question is, what can we understand about the spreading dynamics and the interference of these waves that are, in essence, spreading on this sort of hyperdimensional surface, this network, which is a hyperdimensional surface, and the pathogen and the behaviors are spreading. Anyway, and some of the work I'm going to discuss with you now on group structure and intervening in it and on cooperation is also relevant to the pandemic. Anyway, that's what I've been doing for the last 4 months. But you've asked me to speak to you today, not about that, but rather about some of the work we've done over the last 10 or even 20 years on what I call social network interventions, because humans are embedded in social networks, and these networks obey very particular biological, psychological, sociological, and mathematical principles. And taking these into account offers us tremendous new opportunities to gain insight into human behaviors and also to change them. In fact, we can use an understanding of human social network structure and function to intervene in the world, both in online and in offline networks, to improve human health and well-being across a range of domains. And I'm going to show you a number of experiments we've done in the last 10 years that illustrate this in a variety of applications. And I would say that in the broadest sense, taking our embeddedness, our inevitable, inexorable embeddedness in human social networks seriously shifts our focus to the externalities of our interventions. That is to say, engages us in the study of the response to treatment, not just among the treated, but the response to treatment among the untreated. When we do something to some person or some group of people, how does it affect everyone else around them? That's one of the overarching concerns that we have had. So let me see now if I can advance slides here. We tested it a moment ago. And it's not working. Give me 1 second. Why is it not working? Hold on. There we go. So I'm interested in real social networks, the kind we human beings have been making and embedding ourselves in for tens of thousands of years, and not just the recent online variety. Real social networks look like this. Every dot's a person. Every line between them represents a relationship between two people, whose friend or sibling or coworker, for example. And to my eye, these networks are intricate things of beauty. And they are so elaborate and so complex and so ubiquitous, in fact, that one has to wonder what purpose do they serve? I mean, why are we embedded in networks? How do they form? How do they work? And how do they affect us? And I've spent the last 20 years on this topic trying to understand how and why human beings form social networks and how they affect our lives, our health, our desires, our feelings, our thoughts, and our actions. Now, part of this work has involved exploring the biological predicates and consequences of social networks and the evolutionary basis of social network structure and function. So just to set the stage for a little bit of that and sort of the broader work, and probably at least half of you know what I'm about to tell you on this slide, which is that social networks afford the people within them different structural positions. Excuse me when I look left, because the screen for me is to my right, rather. So I'm not looking away from you. I'm just looking off to the side at the screen. So, so if you look at this image, and by the way, can you see both me and the image, or is it just the image now that you're seeing?
Both.
Both. Okay. So if you look at this image, you can see that I've highlighted, this is a real social network of 105 young people, and they're real ties. Every dot's a person. The lines represent friendship connections here. And I've highlighted 4 particular individuals for the purposes of illustrating the difference in structural position of different individuals. For example, if you compare nodes B and D, B has 4 connections and D has 6 connections. This is known as the degree of a node, and people generally know this about themselves. You have 10 friends, you have 8 friends, I have no friends. People know this about themselves. But there are also higher order properties that people might not necessarily appreciate about their own position within a network. For example, if you compare nodes C and D, C has 6 connections and so does D, but we with this bird's eye view can see that C and D are very different. And I can cultivate this intuition by asking you, who would you rather be if a deadly germ was spreading through the network? And the answer should be D. You'd rather be D. D, you should have the intuition, is less likely to get whatever's spreading and less likely to get it early in the course of the epidemic. They're on the edge of the network. Conversely, who would you like to be if a juicy piece of gossip were spreading through the network? And you'd probably like to be C. And so the difference between those two is known as the centrality of a node, and that can be quantified using a variety of mathematical tools, and probably many of you, or at least some of you, know those tools, and we can discuss them if you want. And finally, if you look at nodes A and B both have 4 connections, but the difference between the two is that the A's friends are friends with each other. You'll see connections between the 4 orange dots that surround A. There are blue lines that connect them, whereas the 4 orange dots that surround B, there are no lines that connect them. B's friends are not friends with each other, whereas A's friends are friends with each other. And this is known as the transitivity of a node, or the probability that your friends are friends with each other. Well, one of the first studies we published now over 11 years ago, beginning to look at the fundamental biological predicates of human social network structure, was a twin study. So we looked at monozygotic twins and same-sex dizygotic twins, mapped their networks, and tried to assess the degree to which, using a classic twin study design, these three properties that I've just mentioned are heritable. And here on the y-axis, I show the percent of the variance explained, or the heritability, and on the x-axis, the three quantities I've just introduced you to. And what we find is that 46% of the variation in the number of friends you have, the degree, is explained by your genes. But we also find that 47% of the variation in your transitivity is explained by your genes. And this is a very bizarre result, because what I just told you is that if Tom, Dick, and Harry are in a room, whether Dick is friends with Harry depends not just on Dick's genes or on Harry's genes, but on Tom's genes. Whether your two friends, Scott and Harrison, are friends with each other depends on Amitai's genes, not just on Scott or Harrison's genes. So transitivity, the probability that your friends are connected to each other, also depends in part on your genes. And
Can I interrupt?
Yeah.
Quick question, Bertram Mahler here. One of the problems with these sort of classic heritability studies is that genes and attractiveness are confounded. And it seems like a pretty good alternative explanation that number of friends and even transitivity of friends is maybe at least partially explained by how attractive people are, and attractive people are maybe attracted to other attractive people. How would you think about that alternative explanation?
So the homophily, the homophily question is a second question, which we'll get to in a moment, that whether attractive people have attractive friends. But there's no doubt that the phenotypic pathway for this might well be, for instance, that your genes make you a bubbly personality, or attractive in whatever way, physically attractive, psychologically attractive. So we're not commenting on the mechanism. We're just summarizing the fact that how many friends you have is partially heritable. But the transitivity results are a bit harder to explain by that kind of a mechanism. And we think that, in fact, this paper, we talk about the so-called attract and introduce model, sort of picking up a little bit on even the language that you just used, which is we show that people, there's a model that can explain the emergence of human social network structure that imagines that people differ in their capacity to attract incoming ties and differ in their interest in introducing those ties to each other. And allowing that kind of a two-parameter model can actually give rise to a human social network structure that looks pretty typical of human beings. So I don't know if I partially answered your question, I think, but I'll come to the homophily thing in a moment and additional results. And if I haven't fully addressed your question, we can absolutely return to it. And incidentally, since I can't see your face and I don't know if you're like looking at me like, oh my God, he didn't answer my question, I have no two-way.
I'm very happy with your answer.
You're happy so far. Okay, you're happy so far. All right, so it's awkward for me. I can't, all the usual cues are gone from this. That's why Zoom, by the way, is so burdensome, I think, for many people, because we have this heightened need to look at people's faces and try to read their body language, but decreased ability to do so because we're using this intermediate technology. So anyway, and finally, we found that even 29% of your centrality can be explained by your genes. So the basic point here is that the fundamental reality of our desire for connection, and ultimately, as I'll show in a bit, our susceptibility to social influence, it turns out, has always been with us. And where you are in this vast fabric of humanity depends in part on your genes. And in fact, my lab has been amassing evidence that it is indeed not a coincidence that we form networks with particular mathematical properties. And we have shown that there is an evolutionary significance to and heritability of social network structure and function. And that phenomena, for example, like peer influence, the mere fact that we want to copy our friends, and homophily have a very ancient, the homophily being the probability that like befriends like, have a very ancient and fundamental significance. And most generally, we would say that across evolutionary time, the benefits of a connected life must have outweighed the costs. And this is an idea I return to in another book called Blueprint, The Evolutionary Origins of a Good Society, that came out about 1.5 years ago. Now, here's another result that we published in a subsequent paper. Here we explored genotypic resemblance, that is to say, the extent to which, if you go into a population of humans, identify friendship pairs, and look at how likely are two friends to resemble each other at the genotypic level. Here we quantified this with kinship coefficients, that is to say, the probability that two alleles sampled at random from two individuals are identical by state. So we have a 500,000 SNPs, or single nucleotide polymorphisms, across the genome for these individuals. We look at this vector of 500,000 in me, then we go to my friends and we look at it in my friends, and we say, how likely are we at any given one of these loci to have the same ACTG allele, base pair at that location? Now, and we do this comparing friends and also pairs of friends and also pairs of strangers within the same population. And then we summarize this by saying, well, what if, how similar would Nicholas and his friend be if they were kin? But they're not kin, they're just friends. And we quantify this using a kinship coefficient. And we find that friends exhibit significantly more homophily, that is to say, positive correlation, than strangers in these genome-wide measures. That is to say, compared to strangers, strictly unrelated friends. And we know these people are not your distant cousins because we've genotyped them. So we can be certain that they're not your cousins. They're not actually your kin, but they are like a kind of, they're not cryptic kin, but nevertheless, they are like kin. They resemble you genetically. In fact, on average, friends tend to have a kinship coefficient that is 0.0014 greater than strangers, a value that corresponds to the relatedness of fourth cousins. In other words, roughly speaking, you go out into the world, you befriend people, and the people you pick as your friends resemble you genetically as if they were your fourth cousins, although they are not your fourth cousins. And we were able, in fact, to show in this paper that those regions of the genome in which pairs of friends have shown greater homophily were regions of the genome as well, which showed more evidence of recent selection over the past 30,000 years. In essence, the toy example I give, and this is, I could give a whole talk on just the genetics and evolutionary biology of human social interaction. So I'm setting the stage actually for the interventions by showing you some of this other work. I hope to interest you. But the toy model we have for this, which is a set of ideas that I won't go into today, relates to this notion of social epistasis. So you probably are aware that epistasis is the idea that the expression of one gene in you might be regulated by variants in a different gene. So for example, the classic example is, let's say I have genes that make my hair go gray, which I do, and made my hair go gray when I was very young in my 30s. But let's say I had other genes which made me bald. Whether I express the gray hair genotype would be partially under control of these other genes which determined whether I was bald. That's called epistasis. But what we're interested in my lab is social epistasis. Inter-individual, do genes in me modify the fitness advantage or the expression of genes in other people to whom I am connected? For example, does the age of menopause in women depend not just on the genes within them, but on genes within their partners, for example? So we have a lot of crazy ideas about this, but one of the toy models I use is that if you imagine that if you're the first person to evolve the capacity for speech in our ancestors, the fitness advantage of that mutation would be extremely limited unless you had friends to whom you could talk. And now, if you could preferentially connect to someone who had the same genetic variant as you, the advantage of that mutation would rise. And what we find in this paper is exactly something like that. That there's a kind of, it looks like, we speculate, a positive feedback loop whereby homophily on these regions of the genome is accelerating the selective advantage of these particular mutations. Anyway, if you're interested more in that, and there's some other speculative ideas, that's in this paper. Now,
can I ask a quick question?
Yes, although this is all preamble to the other stuff.
Okay. Yeah.
Yeah, go on.
Okay,
yes.
I can pause it then.
No, give it to me. And if it's too long,
I'm sorry. Thank you.
No. Ask the question. If it's too long, I'll tell you it's too long. We'll come back to it.
Yeah, no, it's really simple. I mean, so you said, we're sure that people who are closer on this kinship scale are not fourth cousins, but the thing that I've never understood about this type of study has just been how you control for historical factors like, all the Scots-Irish moved to the South in the USA. And so
Yes.
they've got a lot of genes in common because they're all Scots-Irish, right?
Yes, that's called population stratification. And so, for example, if we find that Greeks preferentially befriend Greeks, we should not be surprised at all to find that Greek friends are more alike than, that people have friends that are similar. So, if each of us, for example, pick their friends based on their ethnicity, then by descent, we would have similar. And there are ways to take this problem into account, which we do in this paper and in other papers we published. And this is a very hotly debated field. People always argue it's like your exclusion restrictions in instrumental variable estimation or equilibrium assumptions in economic models. People endlessly argue about whether or not whatever technique you've used is or is not adequate, because you can't. It's all observational. You can't actually prove it. So
yeah, thanks a lot.
You're welcome. Now, if social network structure has genetic antecedents and significance, it begs the question of how ancient this structure is, or whether we can actually document such structural features in human populations living in a non-modernized setting. In other words, what sorts of networks would be formed by ancient humans? Would the networks that be formed, would the sorts of networks that ancient humans made resemble ours or not, given the fact that we now have all this modern technology? So in an ideal world, what we'd love to do is go back 10,000 years and map the social networks of those people. Now, of course, we can't do that. So in this paper, we hit upon the idea of mapping the social networks of a group of people still alive who live like we did in the Pleistocene and also in our ancestral environment, specifically the Hadza hunter-gatherers of Tanzania. There are only about 1,000 of them left. They speak one of the most ancient languages on the planet. It's a click language. They sleep out under the stars. They have no material possessions to speak of. They hunt and gather for their food. And Corinne Apicella, who's now an associate professor at Penn, who was then my postdoc, went into the field. And what we did is we made a photographic census of all living adult Hadza, a kind of Hadza Facebook using 10 years of field photographs. And Corinne would wait near all the Hadza live around Lake Eyasi in Tanzania. You can't make an appointment with a Hadza person. So, you just have to basically stop somewhere and wait for someone to walk by. And like after a week, there's someone. And you go ask them, who are your friends? And they could identify their friends in various ways by pointing to them, as you can see in this image. And by painstakingly doing this, what we were able to do was to map the social networks of the Hadza. And we found a number of things. First of all, we found that Hadza networks look mathematically and visually just like ours. So despite the fact that in the last 10,000 years, we've invented agriculture, we've invented cities, we've invented telecommunications, the networks we make are just like their networks. Furthermore, this supports the idea that network structure, likely has a rather ancient origin consistent with our work on its partially genetic basis. And my lab has done other work, which I don't have slides for today to show you, but I can if you want. Mapping networks in villages in Honduras and in villages in India and villages in Uganda. And again, there are these reproducible mathematical properties, topological properties of networks that are very, very consistent. Furthermore, in this particular study, the dot size and color here corresponds to how cooperative people are. We had them play economic games with real resources, a public goods game where they could be kind to their people to whom they were connected or not kind. And we quantified their level of charity, basically, how altruistic they were, what kind of donations did they make to the public good. And what we found was that so the bigger dots give more money, more resources, and the yellow dots give the most, and the orange dots the medium, and the red dots the least. If you look at this image, you can see that there's clustering within the network of cooperative and uncooperative individuals, as if the cooperative people are preferentially forming niches with each other, or as if by social contagion, my being nice prompts others around me to be nice. And we'll return to this idea in just a moment. Now, in a parallel and much earlier stream of work using both observational and experimental methods, we and others have provided evidence that a variety of behaviors and phenomena, other than germs, of course, which with COVID everyone is interested in, spread within our networks beyond just dyadic ties via processes of social contagion. So obesity, smoking, drinking, and drug use behavior, emotional states like happiness, loneliness, depression, and altruistic behavior, or crime. Andrew Papachristos has done some beautiful work on this. And voting behavior, my colleague James Fowler had a beautiful paper in Nature, a huge randomized controlled trial of 60 million people showing that voting behavior spreads, and purchasing behavior, and of course, ideas. People's attitudes, decisions, and behaviors depend in quantifiable ways on the attitudes, decisions, and behaviors of others to whom they are directly or indirectly connected. And in fact, a very fundamental and key idea about networks is that networks magnify whatever they are seeded with. Networks magnify whatever they are seeded with. So if you put something in a network, it functions like a social magnifying glass. But networks are agnostic. They will magnify Ebola and fascism and violence and fake news. But equally, they will magnify love and kindness and happiness and ideas. And in fact, as I argue in Blueprint, the benefits of a connected life must have outweighed the cost. That there must be some preferential magnification, if you will, of these good properties rather than these bad properties. In fact, as I argue in a very real way, I think that the spread of germs is the price we pay for the spread of ideas. That I come near you to benefit from social learning, but in so doing expose myself to exploitation, violence, or pathogens. But it must be more beneficial for me to learn from you and to work with you than it is for all those other demerits. Let's see here. So let me then show you one of our first, well, actually, before I show you, I want to set the stage with one other basic idea, which is that there's a lot more going on here, obviously, than social contagion. Those things on the previous slide aren't just spreading from person to person. For example, in the contagion of, let's say, of obesity or of academic performance, you know, if you do well academically, does that affect your friends doing well academically? Several things could be going on. For example, the first idea is that there is contagion. There's induction, a kind of social domino effect, such that if you gain weight, it makes your friends gain weight. But a second idea is that it's just homophily, or birds of a feather flock together. That is to say, you know, if people of a similar body size preferentially attach to each other. And a third possibility is that it's neither of those two, but rather it's a context. So for example, you and I are friends, and it's not that my gaining weight makes you gain weight. It's not that I preferentially formed a friendship with you because we had a similar body size, but rather that we jointly share an exposure to a contextual factor like a gym that makes us both lose weight, or a fast food joint, let's say, that makes us both gain weight. And all three of these are typically present in any social phenomenon, and it takes effort using diverse econometric and experimental techniques to tease them apart. Now, here's a very early experiment of ours, published now 10 years ago, to isolate social contagion. We took some data that had been collected by Ernst Fair and Gachter, but that they had not thought to analyze in this way, and reanalyze the data to extract evidence for a cascade effect of altruistic behavior across social ties. So here, imagine what happened in this experiment is that Swiss college students who were strangers to each other were brought into a laboratory, and they were randomly assigned to groups of 4 strangers, and they were given a little bit of money, and they were told that if they contributed their money to the collective, the investigators would double the money. So if I gave $1 to the group of 4, $2 would be divided amongst everybody. I would only get back 50 cents. So I paid a price, but my group has benefited. Obviously, from an individual selfish point of view, the best thing to do is give nothing and hope that everyone else gives maximally. But of course, if everyone does that, the group collapses. And the best outcome is if everyone is extremely generous. Now, what happened in this experiment is that after a round of gameplay, a bell would ring and people would be randomly assigned to new friends. And then a bell would ring and they'd be randomly assigned to new friends, and so on and so forth. And what we realized was that actually this exercise created sequential interactions, a kind of simple artificial linear network between individuals. And what we were interested in is not another difficult topic that has consumed the attention of many scientists for a long time, which is direct reciprocity. Like if I'm nice to you, under what circumstances do you reciprocate the kindness? Nor were we interested in indirect reciprocity. If I am nice to you, is Sarah then nice to me? Rather, we were interested in, if I am nice to you, are you then nice to Scott? And then Scott is then nice to Amitai, and Amitai is then nice to Daniel. Can we foster these epidemics of kindness experimentally? And that is, in fact, exactly what we were able to show. We were able to show, as highlighted in red here, that if Eleni is kind to Lucas in period 1, Lucas is kind to Erica in period 2, Erica is kind to Jay in period 3, and Jay is kind to Brecken in period 4. And this is another one of the more bizarre results to come out of my lab, because what I've just told you is that how Jay treats Brecken depends on how Eleni treated Lucas, even though neither Jay nor Brecken ever interacted with Eleni or Lucas. Here shown experimentally, so it's not due to context, it's not due to homophily, it can only be induction, a kind of ripple effect, a kind of pay it forward phenomenon shown experimentally. And this geodesic spread of kindness through the network is distinct from the temporal persistence, which is highlighted in yellow, such that if Eleni is kind to Lucas, he learns to be kind and is subsequently kind to Erica in period 2, and Lysander in period 3, and Bemi in period 4, and so on. In fact, if you fold back all the downstream kindness that arises, for every $1 that Eleni gives Lucas, the network magnifies whatever it is seeded with. It doubles the downstream kindness from that initial intervention. Now, to be clear, we're affected in another way by social networks. It's not just what's happening around us, whether people are gaining weight or being kind or are happy, for instance, that matters. The actual structure of the network also matters. And I try to cultivate this intuition by asking people to remember their high school chemistry. And as you all learned when you thought about these two objects, you know that they're both made of carbon. And on the left, you have graphite, which is soft and dark. If you connect the carbon atoms one way, that's what you get. Or you take the same carbon atoms and connect them a different way, you get diamond, which is hard and clear. And there are two key ideas here. First of all, these properties of softness and darkness and hardness and clearness do not inhere in the carbon atoms. They are properties of the collection of carbon atoms. And second, which properties you get depends on how you connect the carbon atoms to each other. Connect them one way, you get one set of properties. Take the same carbon atoms and connect them another way, you get a different set of properties. And similarly, the pattern of our connections affects the properties of our social groups. It's the ties between people that make the whole greater than the sum of its parts. In fact, I will argue and I will show you new properties such as cooperation and violence or health and happiness emerge because of the connections, because of the ties between people, and not necessarily because of the people themselves. So it's not just what's happening in people around us that matters. Our experience of the world also depends on the actual structure of the ties around us, near and far. Now, believe it or not, I just spent more time than I wanted reviewing, 10 years of work, and all of that is just a preamble to the real heart of what I want to talk to you about today, which is how we can take advantage of this understanding to intervene in the world to make it better. Because there are three broad ways you can intervene in networks to enhance public health and public policy and to use social networks for good. The first is you can manipulate connection. As I just mentioned with the carbon example, you can change the structure of human social interactions in ways that's potentially beneficial. Another possibility is that you can manipulate contagion. You can change the flows. Given that things spread in networks, how and who can you target to facilitate the spread of desirable properties in networks? And finally, and most recently, and intersecting with some of our work on artificial intelligence, you can manipulate position, changing the location of particular individuals within a network in a way I'll discuss in a moment. And there's expanding science in all three areas using both online and offline networks. I want to give you a feel for some of our results. And these results are all from experiments. Everything I'm about to show you is with bona fide experiments. And we have other findings using observational studies, which which I'm not going to show you today. So over the past few years in the lab, we've developed some software we call BREADBOARD that is integrated with Amazon Mechanical Turk. And it allows you, and can be used in other venues too, but allows an investigator to conduct large-scale experiments with real human subjects with a turnkey ease. We've released this software. You can find it on breadboard.yale.edu. We ourselves have enrolled over 40,000 human participants in the last 5 or 10 years doing these experiments, and many others have used it to do that. And what it allows you to do is it allows you to create temporary artificial societies of real people, and then in a godlike way control their experience, for example, such as the topology of the network they are in and the rules of their interaction, in order to experiment with and study how the structure of networks might matter. And as I said, we've made the software publicly available. Now here is some of our earliest work, 9 years old, that shows the manipulation of connection and how it can affect how cooperative people in a group are. In this experiment, we explored how the rules of interaction in a social system could affect its ability to produce a desirable property, namely cooperation among its members. So using these software tools I mentioned, we recruited 758 subjects, and we randomly assigned them to different worlds, again, to play a public goods game with strangers across multiple rounds of the game. If you look at the lower row, here what happened is we took these, I don't know, there are 20 or 30 people in this group. We dropped them into an Urgis-Renyi random graph with 30% tie saturation. That's the network that you see. That's what it looks like. It sort of looks like a real network, a real social network. It's a good approximation. And the people have different numbers of connections. And we give them some money, real money, and we have them play a public goods game. The dot color indicates whether the people are nice, cooperative in blue, or are mean defectors in red. And in the beginning, on average, across all the experiments, most of the people are blue. About 65% of the people on the first round start by being nice to their neighbors. But across rounds, what we find is people start being nice, but then their neighbors oftentimes or sometimes take advantage of them. And all they can do then is to decide whether to continue to be suckers and give to their neighbors, or to switch and also be defectors and take advantage of their neighbors. So on the bottom sequence, we reproduce a finding that many other scientists have also shown, was that by the end of the experiment, pretty much everyone has become a defector. All the dots are red, except for a few blue dots on the edge there, sort of keeping civilization alive, being nice to each other, isolated on the corner among themselves, preferentially attached to other nice people. Picking up a little bit the idea I mentioned earlier with the Hadza. In a different branch of the experiment, we randomly assigned people to a different topological regime where they played the same game, but now, in addition, every round, they also had the opportunity to rewire their networks, to form ties with some people or cut ties with other people. And in that regime, we were able to show that we could preserve the level of cooperation in the system. The point here is that the rules of engagement specify whether these people are nice to each other or not. It's not the people themselves that's so important. It's the architecture of their connections and the rules for that architecture that determine whether cooperation can emerge in this system.
I'm sorry, can you just explain what you mean by, how are these social networks defined and how do you manipulate them? What does it mean for a person to be connected to somebody else?
So thank you for that. These people are thousands or hundreds, in this case, people are recruited. On Amazon Mechanical Turk, they have a little game interface where they might see their network. I'm trying to see if I can control my slides here, and I can't again. So let me just see here 1 second here. Yeah. And then they're introduced to their friends, their neighbors, for the duration of the game, and they can see them in their little screen. Here are the 3 people I'm connected to, or the 2 or the 4, and then they are asked, do you want to give some money to these guys? And if you do, the money will be doubled, and analogously for them. And so they might say, well, if I'm nice to them, they'll be nice to me, and they can reason out that that's the best thing to do. But then the next round, we show them that you gave money to these particular friends, but they did not reciprocate. And each person in the graph, which has the structure shown in these images that we engineer, we specify that structure. We say, okay, Scott's going to be connected to Harrison and Amitai, and Daniel is going to be connected to Sarah and Scott, and so forth and so on. And then that's for the duration of the game. We engineer that, and we randomly assign people to different spots within this topology that has been specified. And then they play the game across rounds, and we see what happens. Did I answer your question?
Yes, thank you.
Now, in a different branch of the experiment, we do the manipulation I showed you, and what we find is that actually we can engineer this level of cooperativity by, we can experiment to see what kind of topology, what kind of structure of networks is optimal if we're trying to get people to, let's say, cooperate. And then in a subsequent paper, we swept the parameter space for the social fluidity. So we manipulated how much rewiring was possible. On the x-axis, we show the rewiring rate. On the far left is 0%. That's the fixed network I just showed you. In the middle is the modest rewiring, which I also just showed you. But on the far right is 100% rewiring, which is every tie is up for renewal every round. And on the y-axis is a regression-based estimator of the cooperativity of the individuals. And we find, as predicted by theory, this parabolic shape. In essence, what we find is that in fixed networks, cooperation disappears. If you're stuck with people and they start taking advantage of you, cooperation disappears. Similarly, in networks in which there's entire social fluidity, cooperation is not sustained. Why? Because why should you be nice to people if they're here today and gone tomorrow? If every moment, every one of your social contexts is changing, and it's in the middle regime of social fluidity that you optimize cooperation. We believe that this illustrates the utility of a number of social institutions. I'm only going to speculate on one given the time, and that's for example, marriage and divorce. In a society in which divorce is impossible, if your spouse is really abusive, you have no reason to be nice to them either. You become abusive, and so the marriage collapses. Conversely, in a society in which divorce is too easy, and you have a new spouse every day, let's say, similarly, you don't make investments in your spouse. So we want an institutional regime that makes marriage, divorce easy, difficult but not impossible to optimize the investment, let's say, that spouses might make in each other. That's a speculative illustration of this idea, and there's some others which we can return to if you want. Now,
can I just ask a quick question related to this, that example that you gave, and sort of back to the experiments that you.
Hello, you broke up there. I don't hear you anymore.
Like contagion. What's that?
You were lost there for a moment to me, so I didn't hear your whole question. Say it again, please.
Okay, I'm curious what the degree of specificity is in the sort of contagious cooperation. Like, will it transfer from one task to a different task? Or is it pretty specific to an individual?
That's a great question.
Paradigm?
That's a great question. I don't know the answer to that. And if you're a graduate student and you want to come to my lab and do a postdoc and study questions like that, we always are hiring people from time to time. But we haven't looked at task transfer. Dave Rand has looked a little bit at this across other domains of cooperation and published some papers. You probably know Dave Rand. He's now at MIT. But I haven't looked at it, and I don't know the answer. We have, I mean, Dave has looked at different kinds of public goods games, prisoner dilemma games, but they're all kind of in that flavor. He hasn't looked at, for instance, if you score highly on this game, will you also be more likely to give blood, for example, or engage in some other kind of model of altruistic behavior. Did I answer your question?
Yeah, thank you.
So in this vein of manipulating structure, here's still another experiment of ours, manipulating another feature of social interactions. This now was published about 5 years ago. And I don't know if you can see the citations, but they're at the bottom of the slides. Are they visible to you? Yeah, okay. So I won't repeat you can just copy them or whatever if you want. But anyway, we recruited 1,400 subjects and dropped them into 8 sorts of artificial societies. And here we were interested in the causes and consequences of economic inequality and wanted to approach the problem experimentally. And so what we did is we took the same amount of money and we manipulated how it was distributed in these groups. Did everyone get the same amount or did people get differing amounts? And we specified a Gini coefficient, a measure of inequality of, let's say, 0.2, which is sort of, 0 is everyone has the same, 0.2 is sort of Scandinavian inequality, and 0.4, a Gini of 0.4 is United States or Morocco inequality. And but the total amount of capital was fixed. We just distributed it according to this distribution, and we randomly assigned people to be rich or poor in these societies. And furthermore, we manipulated whether you could see or not see the wealth of the people to whom you were connected. And it turns out that by manipulating visibility, we could gain a number of insights and achieve a number of objectives. And if you look here, we find that in initially unequal conditions, visibility has a number of interesting effects. So for example, if you look on the left here, in the invisible condition, the dots are people, the ties are these connections that we've artificially induced and introduced people. The size of the dot is the amount of wealth that the people have, and R is whether they were randomly assigned to be rich at the beginning, and P is whether they were randomly assigned to be poor at the beginning. And the color of the dots is our usual convention. Red is defectors, blue is cooperators. And what we find is in the invisible condition, where people can't see the wealth of their neighbors, after a number of rounds of the game, everyone has become rich, all the dots are big, and most of the people are cooperators. Most of the dots are blue. And the inequality has declined from 0.4 to 0.14, which is a very low level of inequality. In a different branch of the experiment, when we flip a switch and make the wealth visible, we find none of those beneficial effects. If you can see the wealth of other people to whom you're connected, you are not able to cooperate with them to reduce inequality or maximize wealth. And in fact, here's how inequality and visibility affect the accumulation of wealth in these societies. Across groups, on the y-axis is the average wealth of the groups or the societies. On the x-axis is the round or time. There are 6 treatments, whether the initial inequality is none, low, or high, and whether the visibility is visible or invisible. A 2x3 factorial design, you can see all the trajectories of different societies. And the punchline here is that manipulating the inequality didn't seem to affect the capacity of these societies to produce wealth, but manipulating visibility did. And that invisibility made these societies better off. Now this, I should say, broke my left-wing heart, because I thought for sure that inequality would be really bad for these societies, and I was not able to document that experimentally. Basically, societies can be unequal, but what's really corrosive is if you can see the inequality. If you can see it, it's bad. If you can't see it, it may not be so bad, at least in this experiment. And also here we look at cooperativity and find similar results in terms of how nice people are to each other. Depends very sensitively on whether they can see the inequality, but not so sensitively on how much inequality there is. And these findings have implications speculatively for policies as diverse as pay secrecy in firms. You know, basically what we believe is that if people make similar amounts of money, a firm should advertise what everyone makes. But if there's high levels of inequality, publicizing pay packets will corrode the cooperativity of the firm. And also, for years, I thought that school uniforms were like fascistic. You know, like I was really opposed to having kids wear uniforms at school because it just didn't sit well with me. It felt, you know, like, I don't know, like it just wasn't what I wanted. And that people should be able to express their individuality. But actually, if you think about school uniforms, they are like a kind of invisibility cloak, right? They conceal displays of wealth and may in fact, therefore, enhance cooperation and learning and a sense of collegiality, possibly. I don't know, we need to do experiments. Now, here's another result on the importance of network structure. So we're still talking about structure, like manipulating structure and features that have to do with connections between people. We've become interested in the sharing economy and ways of optimizing it. And we built a model system that captures some pertinent features of the challenges of sharing. Here we imagine that wireless routers in people's homes, they have wireless routers, and that people can share their excess capacity in the expectation that others will reciprocate. People are dropped into a grid, a neighborhood grid. They're given some router capacity, and they're told, like, you can't use this capacity for yourself. Do you want to share it with your neighbors or not? And in this game, people choose whether to do that. And we can measure quite a bit about this behavior, including how often the exchanges are reciprocated and how satisfied the players are with their exchanges overall and at the end of the game. Now, this paper introduced the game, but I don't want to tell you the results of this paper. Instead, I want to tell you the results of a different paper where we use this game, this scenario, but we assess the satisfaction with sharing. And what we did in this paper is we manipulated the network structure, just like the carbon example I gave you. 600 people in 40 groups of 15 were asked about their satisfaction playing the sharing game at the end of the game. And we dropped them into two networks in which we manipulated a property of networks known as the degree assortativity. Degree assortativity is homophily on degree. Do popular people befriend popular people and unpopular people befriend unpopular people? That's a degree assortative network. Or is it the reverse? Popular people befriend unpopular people and vice versa. That's a degree disassortative network. And that's, for example, how the airline network is organized. And certain neural networks are organized as well. So, but what's interesting about this experiment is that both of these, and you can look at these pictures, and on the left you have a degree disassortative network, and on the right you have a degree assortative network. Both of these networks have 15 nodes and 18 edges, and they have exactly the same degree distribution. 6 nodes have 1 tie, 3 nodes have 2 ties, 3 nodes have 3 ties, and 3 nodes have 5 ties. So the degree distribution is the same. How, there's exactly the same number of people with the same number of ties and the same number of people and the same total number of ties in both networks, but the arrangement is different. And what we find is that the collective welfare in this experiment was improved by arranging the networks to form ties between people with similar degree. By engineering a degree assortative network, we can make people happier, even without increasing or redistributing any resources. The structure matters. The structure of interactions matters to collective properties of the network. Okay, so that's a quick review of some, and that was our most recent paper on structure. That paper came out a year ago now. Now let me shift and tell you a little bit about contagion experiments, then position experiments, and then I'll close with a big idea. So here's a paradigm of experiments that we're conducting, illustrating how one might manipulate contagion. And this is, imagine this is a set of villages in the developing world, although the same principles could apply to sets of classrooms or workplaces or hospitals or online. So in these villages, you have 2 villages and who they're people and who they're connected to. In the right-hand village, you pick 6 people at random and you give them a public health intervention, those 6 yellow dots. And in the control village on the left, you don't treat anyone. The usual perspective in public health is that you come back a year later and you go to those 6 people and you assess how many of those 6 people adopted the intervention. So maybe you treated 6 people, 3 people adopted the intervention. And, but that's not what I'm interested in. I'm not interested in response to treatment among the treated. I'm interested in response to treatment among the untreated. What does everyone else in the village do when you give those 6 people the intervention? Maybe 3 of the 6 treated people adopt, but maybe they persuade 3 of their friends to adopt. And in the control village, for a total of 6 in the treated village, and in the control village by secular change, maybe 2 people happen to adopt the practice. But you should have the intuition that now we don't have to pick the 6 people at random. Maybe, for example, we can pick 6 central people in the network. And now instead of 3 of the 6 people respond, but maybe they recruit 30 of their friends by virtue of their structural power in the network. So same village, same intervention, same number of people targeted, maybe 10 times the effect because of who you pick in the village to target. Now, mapping the network is not always feasible. It can be expensive or impractical. And so the question is there a way to identify influential individuals without having to map the network of ties in a whole population? And because of time, and because I'm so long-winded, and because we've taken questions during it, I would like to skip, with your permission, a detailed description of the friendship paradox. Basically, here the idea is that your friends have more friends than you do. And the citation is here, and this is based on some work by Scott Feld in the American Journal of Sociology like 30 years ago, a nifty little paper. We took this paper and we applied it. And basically we said, you're going to go into a village, you're going to pick people at random, you're going to ask them who their friends are, and you're going to treat their friends instead of treating them. So if you pick the 6 yellow dots at random, their friends on average are the orange dots, and those orange dots are more central in the network. And the reason this is so valuable is that you can identify the orange dots without mapping the network. You don't have to map it. You go into a village, you pick people at random, and then you treat their friends with the intervention rather than treating them. We've done this many times now. In India and in Honduras, I'm just going to quickly show you some results from our experiments in Honduras. This is where we work. It's a very poor part of the world. People here live on less than $2 a day. These are these little village hamlets. They're mountainous. The villages are sort of densely connected among themselves, but not with other villages. And we've created software that allows us to map the networks of the villages. We call this software Trellis. We also make this publicly available at trellis.yale.edu. And this addresses a host of challenges in collecting network data in these types of challenging situations, for example, with low literacy, or with what we call the Maria Hernandez problem. And that problem is that if you go into these villages and you ask people, who's your friend, many of the women will say Maria Hernandez. Well, which Maria Hernandez? 20% of the women are called Maria Hernandez. And so you got to figure out which one it is. This allows you to do a photographic census. And then as the women say Maria Hernandez, it brings up a picture of all the Marias. They can point to their friend, just like that Hadza study I showed you, which was an early work, but now computerized. So this was our first field trial, which we published in The Lancet in 2015. And we mapped the networks of all the adults in 32 villages. And we randomly assigned 32 whole villages, which was about 5,000 people, to one of 3 different targeting algorithms. So in all the villages, 5% of the people were chosen to get a public health intervention, which was a multivitamin and a clean water intervention. In a third of the villages, the people were chosen at random. The 5% were chosen at random. In another third, the 5% were chosen who had the highest degree. And in a third, the people were chosen according to the friendship nomination technique. And the question is, can we move a whole village and not just individuals to change their behavior? Given a budget constraint, who do you target? If I can pick the crucial 5 or 10% of people in a classroom or in a village or in a workplace to target with an intervention, who do I target so that all of the others might copy them? Just like if you're a bioterrorist, who do you infect to get the most secondary infections? You don't infect a hermit up in a mountain. You want to infect someone with a particular location. And we had 2 public health interventions. As I said, here's one of my graduate students, Allison Huang, at the time, delivering the intervention. And here is how you might target the nodes in one illustrative village. This just illustrates the difference between the orange dots, which are 5% of the people chosen at random, and the yellow dots illustrates the 5% that might be chosen because they had the highest degree. And here's a slide of some of our most basic results. On the x-axis is the days since initial targeting. These are adoption curves. And on the y-axis is the proportion of people who've adopted the multivitamin intervention. And to make a long story short, nomination targeting outperforms these other types of targeting that we could have used. And that by the end, we can get 75% of the people to adopt the multivitamin intervention by using friendship targeting. Now, we followed this up with a huge study that we haven't yet published from, supported by the Gates Foundation. It's a randomized controlled trial of 176 villages and 30,000 people in the Copan region of Western Honduras in partnership with the Ministry of Health and the Inter-American Development Bank. We mapped the social networks of all these people in all these villages, and we randomly assigned them to 16 different treatment groups, a 2x8 factorial design, where we manipulated what fraction of people were given the intervention in each village, between 0 and 100%, and whether they were chosen at random or by friendship nomination. And the intervention was an 18-month maternal and child health intervention, a standard intervention developed by others. We weren't interested in proving, does that intervention change the behavior of the people who got the intervention? We were interested in testing what is the minimum fraction of people and by what means should you choose them such that if you target those people, everyone else will copy them. So this illustrates what we imagine could happen on the right-hand side here. So on the x-axis is the percent of people targeted, and on the y-axis is the percent of the people who respond to the intervention. The x-axis goes from 0 to 100%, and the y-axis goes from 0 to 50%, because in almost no public health campaign does 100% of people get infected. Even with epidemics, 100% of people rarely get infected. So if there's a linear response, if there's no social effect, if you target 100%, as shown in the purple line, if you target 100% of people, 50% might respond. Or if you target 40% of people, maybe 20% respond. Now, of course, you guys know that that's not usually what happens. Usually you have the S-shaped diffusion of innovation curve, and there's a social effect, a nonlinear response. So at low percentages of targeting, the non-adoption by other people in the village suppresses your adoption. You're less likely to adopt because you look around and your friends aren't adopting. But then you reach a critical threshold and an inflection point, and now the social effect works with you. And so now you get super linear response because your friends have adopted in addition to your being treated. And you get this curvilinear effect and then a plateau. Our question is, can we shift that curve to the left with enhanced social effect as shown in yellow? If we shrewdly pick 20% of the people, is it as effective as if we had picked 100%? And the answer is yes. These are unpublished results. This shows, I forgot what outcome this is. This is something to do with how umbilical cords are treated, are taken care of by women in these villages. Just the bottom line is the red curve with friendship nomination is shifted to the left. We'll be publishing these results in the coming year or two. Now, finally, I'm going to tell you a little bit about position interventions, and then I'm going to close with a big idea. And because I've been speaking extra fast the last 20 minutes, we're going to end the talk roughly on time, and then we'll have some time for questions. Is that okay?
Yep, that's great.
Is all right? We can go on like this. I can't see you, so it's hard for me to judge whether I'm just speaking into the ether. And if you were yawning or combing your hair or whatever, I have no way of knowing what you're doing right now. So anyway, I'll keep talking. So this is a very recent experiment of ours. Actually, it's 3 years old now, that involves the manipulation of position and some other ideas involving the use of artificial intelligence. And we're exploring the performance of groups engaged in the collective coordination tasks and not just cooperation tasks. Now, let me, before I speak further, illustrate with a very toy example what a position intervention is. So we talked about how you might manipulate connection, which is the wiring diagram. And we've talked about how you might manipulate contagion, which is who you target to facilitate the flow of something in a network. But now with position, what do I mean by that? Well, imagine you are a classroom teacher and you have 20 desks in front of you and they're nailed to the floor. And outside the door, you have 20 students of differing ability. The question we're interested in is that the desks nailed to the floor are the topology of desks. You can think of as the social interactions of the students. You know, who's connected to whom based on their spatial orientation of the desks. Now you have 20 students of differing abilities outside the classroom. And the question is, where should you seat the students so as to maximize learning in your classroom? Should you put all the bright students in the front row or all the bright students in the back row? Or should you mix them up, for example? So this is a position intervention. Given an ensemble of nodes, given a fixed topology, given an ensemble of nodes with different traits, where do you put those nodes in a graph so as to enhance some collective property like cooperation or well-being? Very different than all the other things I've talked to you about so far. In this initial experiment, we shifted from a cooperation to a coordination task, and we used a classic example, which we did not invent. This is Michael Kearns's application. He's a computer scientist at UPenn, of a color coordination game. People are dropped into a network as shown in the upper left, and they are randomly assigned a color. And here the colors are orange, yellow, and purple. And they are told there are 3 colors. They're told you can switch colors as often as you want, and your job is to pick a color dissimilar from your neighbors. And if all of you are able to converge, work together and converge at the end, so you all have different colors, you will all get paid. But if you're unable to work together and coordinate on a solution, none of you are paid. So people look at their immediate neighbors and they're trying to resolve color conflicts by flipping their color to minimize the number of conflicts they have with their neighbors. The red lines indicate 2 connected dots that are in conflict. They have the same color. And the purple lines indicate that along that underlying topology, those 2 dots are not in conflict. So you can see across time at 0 seconds, there are 12 conflicts, 12 red connections. By 105 seconds, the people have worked together to resolve to just one conflict, the 2 yellow dots in the middle, but now they're stuck because the yellow dots can't switch. If they switch to purple or orange, they will increase conflicts because they have more purple or orange dots. So one of them has to do that. One of them has to make this counterintuitive move and increase conflicts. And they in fact do that. And by 245 seconds, this group has solved the game and they get paid, as shown in the upper right. On the bottom panel, we plot the objective function here, which is the number of color conflicts on the y-axis across time. These games last 5 minutes on the x-axis. And there are 2 kinds of conflicts. There are resolvable conflicts, which is shown in yellow, which is a move a person can make and resolve the conflict, but also, as shown in orange, irresolvable conflicts, that they're stuck. And for example, if you look at 105 seconds, that dotted line, you see there's one orange, the histogram shows one orange conflict, and it's irresolvable. There's no move the 2 yellow dots can make that easily resolves the problem. And we did this experiment with 4,000 people in 230 groups. And because we're sneaky, what we did is we experimentally manipulated, we replaced 3 of the people with bots. And we endowed these bots with simple artificial intelligence. Specifically, we made these bots so that they were slightly noisy. And that is to say, they deliberately made mistakes. Either they had 0% noise, as shown in the first column, which is every 1.5 seconds, they looked at their neighbors and they switched to a color that numerically minimized conflicts. Or they had 10% noise, which means they did the same thing, but 10% of the time they picked a color at random. Or they had a lot of noise, 30% noise, which is they did the same thing, but 30% of the time they flipped and picked a random color. And then we manipulated in the rows whether the 3 bots were put at random in the network, or were they positioned in the center of the network, or they were positioned in the periphery. These are survival curves. On the y-axis is the fraction of groups that have resolved the game. And on the x-axis is time. So if you pick, for instance, the middle of the 9 panels, and you look at the orange line, those are the results for the 30 groups that involve just humans. So 30 groups of, 16 humans trying to resolve the game. At time 0, 100% of the groups have not resolved. And then as time goes by, more and more groups resolve, so that by the end, 66% of the groups have solved the problem if they're just humans. But if we add bots with a little bit of noise to the middle of the network, we can improve the ability of the people to solve the problem. Both perfect bots and 2 noisy bots were unhelpful, but adding these little bots allows the people increases the speed of solution by 50% or more. Now I'm going to skip this slide because it goes into we showed that the bots were especially helpful when the color coordination task was difficult. And I'm also going to skip this slide, which talks a little bit about how the bots worked. And they worked not just by making it easy for the people to whom they were connected to solve the problem, but also they created positive ripple effects throughout the network. That's what the results on this slide showed. And we're building on this design of adding simple bots to other situations that involve social dilemmas and collective action problems. We want to explore whether simple programming, what we call dumb AI, might be able to help people overcome social friction in a variety of coordination challenges. Not just the noisiness of the bots, but also their style of play or other sorts of things that they can do. And we just had a paper, we've had a number of papers recently, one in PNAS a year ago, with Brian Scazzoletti's lab, he's a roboticist, and one in iScience that shows that a little bot that rewires ties in networks can improve the cooperation of human groups. And the gist of what we're doing is we want to look at coordination, cooperation, evacuation, navigation, sharing, all these challenges that people have. Can we, by adding a few bots to the system, make it easier for the people to help each other? So we're not focused on developing super smart AI to replace human cognition. I couldn't do that anyway because I'm not a computer scientist and that's not our expertise. Rather, we are focused on developing not super smart AI to replace human cognition, but rather dumb AI to supplement human interaction. If we take these dumb bots and put them in the midst of smart humans, all the bot has to do is make it a little bit easier, like a catalyst, like simulated annealing, like activation energy in chemistry. You just have to lower the barrier to the people to work collaboratively with each other. Okay, that's the end of my experiments. I'm going to close with one final idea. It just take a couple of minutes, and then we'll still have 15 minutes for questions. And this is an idea that is about what it means when we intervene in a social network, because I think such interventions provide us with a way to manipulate social capital. And to understand one sense of this, consider this idea. What's the point of a connected life? How does it help us as individuals and as a species? And it turns out that networks are a resource that we can all use. Networks are a kind of social capital. Now, most people, when they think about capital, think about money. But really, capital is any stock of resources that can be put to productive use. So it's a stock that you can do something with. And two further key ideas about capital are that in order to create capital, you have to invest skill and effort. You have to know something and do something in order to create capital. And second, and more subtle, and in an idea that I've been thinking about for 20 years and I'm still not satisfied, is that in order to create capital, you have to make changes in a substance that make it yield a higher rate of return than it otherwise would. That fundamentally, the capital creation process is about manipulating the world to transform one thing into another thing, to make changes in a substance that make it yield a higher rate of return, that make it more productive. For example, a farm is a stock of capital. By investing labor and skill to clear the forest, we can make the land more productive of grains and flowers and vegetables, for example. So land, especially improved land, is a form of capital. Or think about this. You can take this tree, invest skill and effort, and mill it into lumber. And the lumber is more valuable than the tree because you can do things with the lumber you couldn't do with a tree. Namely, invest still more skill and effort and convert it into a violin. And the violin is more valuable than the lumber because you can do things with the violin you couldn't do with the lumber, namely make music. So at each step of the way, we invest skill and effort, we transform one thing into another thing, and that imbues it with this productive power, this ability to do new things that reflects what capital is. So capital is a change that allows a substance to act in new ways. And this is part of what makes it a store of wealth and a source of productive power. Now, in the 1960s, a key innovation took place in the social sciences to begin to see people and their skills and talents as a kind of human capital. And a chief example of this is education. So, for example, you can take this dissolute former graduate student of mine who's now a professor at UMass Amherst, who's a drunkard, let's say, and invest skill and energy and clean him up. And in the middle now, he's more productive and capable of doing things he wasn't able to do, such as invest still more skill and effort and give him an education, here a Columbia University education, and make him even more capable of doing things he was not previously able to do. So if we can endow someone with skills and knowledge, we have changed them and they've become more productive. And so this is in essence what I'm doing right now. I'm investing skill and effort, and I'm working on the neurons of your mind. I am transforming your brains, I hope and imagine, and making you more capable of doing things you were not previously able to do, such as understand and talk about social networks. Well, just like physical capital is created by a change in the material world, and human capital by a change in persons, social capital in organizations, in companies, in communities, in fact, in our whole society, is a change in the relations among persons, a change that renders the group more productive and capable of doing things it was not previously able to do. And that, in fact, is the deepest account I can give you of what social networks mean for our lives and why it is that we can use them to make our world better. Thank you very much. I know clapping is so awkward on Zoom, it's ridiculous. Let me see if I can stop sharing my screen. So stop sharing. And let's see, escape here. Or, okay, did I stop sharing the screen successfully? Yes, okay. And so now I can see you all again. So you're all on this view, and I'm available for questions, which I won't be reading the chat. So if you don't mind, just raise your hand visually or speak up, like as if we were really in person.
All right, I'm visible now, so I'll speak up and I'll even have some facial reactions. So one of my questions is that the hunter-gatherer study and many of the Amazon Turk studies work with small networks, reasonably small. Obviously, our evolutionary origins are in roughly small groups. One of the challenges we have in modern life is these uncontrollable vast societies of strangers, and I don't have to tell you all the stuff that comes with it. I'm curious what your thoughts are about intervening on something like the US and its enormous polarization, and it's getting worse, and it will get worse even further. Do we just have to split up into the small groups and then have mini societies and not care anymore about the others, as it happened in Europe for a long time? Or are there other ideas that you have for dealing with this?
So there's quite a few things embedded in that. First of all, the way we live in these vast networks, of course, is specified and guided by our evolutionary past where we lived in small networks. So you're absolutely right. We take this ancestral apparatus and we're applying it now in these larger scale societies. 100% correct about that. But we have begun to do a bunch of things with our experiments to begin to think about how to release some of these bots into the wild. For example, we have some bots that we imagine can reduce racist communication online. There was a fantastic experiment done by, I'm blocking on his name right now. He was a brilliant graduate student at NYU, and his paper is called The Tweetman Effect Among the Tweeted, or something like that. It's a witty title in the Journal of Politics. And he found that you could create these, they were actually not bots, they were puppets, sock puppets, accounts, where he could intervene in racist invective online, in real life, on Twitter, and reduce racist expression online. And we have some ideas about how some of our bots, in a very distributed fashion, could reduce the flow of, could act like traffic cops, retarding the flow of fake news and enhancing the flow of accurate information, working locally. I didn't show you today, we have this other bot that can, just working locally by engineering the ties around you. This paper was just published in iScience. Shirado is the first author, Hiro Shirado, that can rewire the networks around you and foster cooperation on a big scale, even though it's only working on a small scale. So the second part of my answer is going to be that that I do think it's possible to use some modern technologies to respond to some of the challenges that modern technology is also imposing on us. But the last point you had was about whether we would be better off splitting apart. First of all, in my book Blueprint, I talk a little bit about how there's a long history going back to the Roman times of people saying, in like kibbutzes, for example, in the 1960s, and people saying that, society's screwed up, let's go and form a new society. And the bottom line is they wind up reproducing the same exact society that they had originally. I don't think fissioning is a realistic solution for our dilemmas. I do agree with you that if we could only have societies of, let's say, 10 million people, it might be better, but even that is a huge number. And I don't think, given the benefits of urbanization and of nation states, despite the costs of urbanization and nation states, I don't think we can go back to living like hunter-gatherers. So I didn't give you, I know, a great answer, but I answered some aspects of your question. Is there anything you'd like me to continue on?
No, just the one struggle that I have is that our societies are not just much larger, they're also much more hierarchical. Hunter-gatherers are for the most part egalitarian, and maybe that's what it might take despite the size.
I talk about that. I'm not sure I agree with you. Depends on how you quantify hierarchy. If you use the Gini coefficient of wealth inequality, then yes, you're 100% correct. So people have looked at the inequality of hunter-gatherer populations, and they're about order 0.12 is the Gini. There is some inequality. And that partly, I think, reflects the workings of the natural lottery. I mean, some people are born stronger or smarter than others, and you're never going to have perfect equality. Just even if you efface the social lottery, you're still going to have the natural lottery. But of course, modern societies, through the market, can exacerbate that, right? And now I think the market is a fairly, I believe, fairly neutral and beneficial phenomenon, although there's market failure, and of course I recognize that, and we can talk about that. But in terms of hierarchy, all societies have hierarchy, and I don't know whether we have institutions of political power, so the president but the president is not more powerful, let's say, than King Fahd, or the Crown Prince of Saudi Arabia, although that country only has 300,000 citizens. So I don't know how much hierarchy we have. Other questions?
I have a question. My internet connection is a little bit unstable, so hopefully this works. But so I'm not going to show my face because of the internet.
I can't see you. You're just a disembodied voice, but go on.
So my question, so you've shown, I think, pretty convincingly that this social capital of connectivity is a useful tool to spread connectivity and health. But I could imagine it could also be used for marketing purposes or to spread misinformation. And I'm wondering, as these tools develop that allow the social capital of connectivity to be manipulated,
Yes.
if you have any ideas
Yes.
or suggestions for how people can protect themselves from governments using those tools.
No,
Or,
it's very bad. It's very bad, and it is a dual-use technology like any other technology. We invent guns to hunt and then we kill each other, or nuclear power and then we bomb each other, or medicines and we poison each other. And like any technology, it can be used both ways. And of course, in my lab, we always have these very happy, we're improving cooperation, we're improving public health, we're increasing vaccine behavior, but you can use every single one of our things to do the opposite. And it may not surprise you to know that, a number of government agencies and military groups and countries around the world have been, reverse engineering some of these technologies, not just firms to sell you useless products, but for example, I'm sure the military is using some of these ideas to degrade cooperation among, Al-Qaeda cells, or and I believe that the Russians, I was not a co-author on the paper that my long-term collaborator James Fowler did with voting. It was on the cover of Nature, I think in 2015 or something. James did this landmark paper using Facebook, a randomized controlled trial on voting behavior. And I'm pretty sure that the Russians read that paper and weaponized it against us. And it's very much in keeping with Putin's training in judo, which is using the strengths of the enemy against him. We're an open society, we're a technologically advanced society, and what a brilliant maneuver to use Twitter and Facebook against us and to sow dissension. So yes, all of these tools can be used for evil, 100%. And the power of individuals to resist that is limited, unfortunately. That's a depressing answer.
No, it's fine. And I don't want to make you feel like I'm like picking on you. I think the research is amazing and it's fascinating and awesome.
There's nothing you could do to make me feel picked on. I love intellectual debate. I'm used to being teased in my family. I grew up in a Greek family where to tease someone was to show affection, and I hire graduate students who are smarter than me because I think that's the only way I get smarter. So there's nothing you can do to. I might not respond to you if you were rude or something, but other than that, yeah.
Well, thank you very much.
Other questions? I can't see you.
Hi, I had a question about some of the historical results you show. You're just suggesting that these kinds of networks that we see in modern societies are also prevalent, perhaps in earlier hunter-gatherer groups. And, the first time that question is that surprising? Like, it seems like this network description is flexible enough that it could describe lots of different things, even things that are very dissimilar than us. But I was more interested in are there ways in which these networks are constructed that have changed over time, like the ability to transmit information efficiently or something? Are there ways in which we can see the developments of networks optimized for certain levels of productivity or something?
I'm not sure I've understood your question fully, but as far as we can tell, using a family of parameters, for example, the simplest thing you could do is just quantify the degree distribution. And if I quantify the degree distribution among the Hadza and compare it to the degree distribution let's say in American towns, it follows the same shape. Or you look at transitivity. You measure, well, how common is it among the Hadza that your friends are friends with each other? It's the same as with us. Or you measure decay with geographic distance, and you find that people are, every additional day required to reach your friend, something like halves the probability that you're friends with that person. Now the Hadza have to walk for 20 miles. It takes, so, people live even further than 20 miles away, but we can fly. So you have to account for the ability to reach them. Or we look at reciprocity. What's the probability that if you nominate someone as your friend, if you say Joseph is your friend, and then I go ask Joseph who his friends are, there's a 30% probability he'll say Harrison is his friend. Joseph doesn't know that you said he's his friend. You don't know that vice versa. That probability is the same in the Hadza and in us. And on and on and on. You can do this thing called fingerprinting of network, looking at network motifs, which is, what are the microstructure of the networks, the patterns, the small scale patterns, same in the Hadza and in us. And we've done this now in many other locations, not just in hunter-gatherers, but as I said, in Indian villages, in Honduras, in Uganda, and so on. And again, we find these patterns. So my argument is that friendship, it's like, if you look at the function of people's pancreas, the function of the Hadza pancreas and the Indian pancreas and the American pancreas and the Honduran pancreas on average is the same. And that's sort of the argument I'm making. There's some deep and fundamental properties. And then in fact, our evolution affects not just the structure and function of our bodies, not just the structure and function of our minds, but the structure and function of our societies, which is...
I think that's fascinating. My question was more about, are those good degree distributions?
Now that is a very good question, as known to God, for example. And I think, let me give you one illustration of that point. So I do believe that that natural selection has worked on the topology of human graphs, that the topology we find in humans has been shaped by natural selection. For example, to optimize the flow of information while minimizing the flow of germs, okay? How do you arrange a graph such that you got to have these complicated trade-offs, cooperativity, idea flow, germ flow, violence, etc. So here's a simple example that I'll give you. It'll take me a minute or two to set this up. So remember we talked about degree assortativity and disassortativity. So in degree assortative, popular people are connected to popular people, or airport hubs are connected to airport hubs, and unpopular people are connected to unpopular people, or small airports are connected to small airports. And of course, airports, it's not the case. It's degree disassortative, okay? Or people could be, popular people are preferentially connected to unpopular people and vice versa. Now, think for a moment, everyone on this audience, think for a moment, which of those networks, degree assortative or degree disassortative, would be better for the transmission of germs? If I gave you, remember, let me share my screen again. Let's see, share screen, share. And I don't know if you can see my screen again. Can you see my screen again? Yes, okay. So let me just quickly go back to this slide. If you were, God or natural selection, and you could arrange a group of people in one of these two networks, which of the two would be better for the flow of germs? Degree disassortative.
Yeah, that's what I guess.
Yeah, degree disassortative. Because if, for example, if you think about the airport network, if a bioterrorist infects someone in New Haven, then the next hop, that person is going to fly to Chicago, and then from Chicago, it's going to spread everywhere. All right, but if you had a degree assortative network, pathogen epidemics that began stochastically in the graph somewhere at random will tend to be restricted to their region of the graph. So of all the ways you could arrange networks, endowing them with the property of degree disassortativity would confer on the group some relative immunity to the spread of pathogens. I don't think it's a coincidence that we evolved to have degree disassortativity. I think that property was selected for. And that's why when you go anywhere around the world, social networks are degree disassortative. That's the argument. Now, it's very difficult, of course, to prove that. But that, I think, addresses your question, which is, are there features of networks? And the same, I won't go into it because it'll take too long, goes with certain other things like transitivity and reciprocity. Shall we do one more question, Jae Young? I don't know how to organize. I mean, maybe I should let you take charge. It's 4:30 and I want to be mindful of people's time. But I know I'm going to be with you from 5 to 7, I think, doing some meetings with some individuals.
That's right.
I'm also happy to spend another minute or two if people want, and I need a short break, but I'm available right now.
Sure. So for folks who have to leave, thanks for tuning in. And if there's one more question for Dr. Christakis, I think I saw Oriel raise her hand. No? Then
I have to go to a meeting, but I'll be back at 5.
All right, Oriel, thank you.
I'll see you at 5. Bye.
Anyone
but yeah,
else?
there's another question. I think we have time to take another.
I'll ask a question if there's
okay.
some. So actually one thing I've always been curious about is I know like the topology of networks change the flow of information. But I was wondering if your lab has done any work to address sort of whether the structure of networks change the way that humans process information. Like, I guess one thing I've wondered about is if something like homophily plays some kind of normative role where if you're more connected with people that that you're more similar to, that reduces uncertainty and that allows you to like coordinate better. So in some way there might seem some like normative benefit to being
Yes.
around people that you're more similar to. So I wonder if like, you know, in the social media era, like something we probably see a lot of is ideological homophily. And if that in some ways can make people like dumber or smarter, I don't know, either it can go either way, right? So I was wondering.
So that's an excellent question, and I have given some thought to that. Some of that is discussed in Blueprint, and also we have a couple of papers on homophily, which I blew by today. One was that paper in PNAS, and another is a theoretical paper that an applied mathematician, former postdoc of mine, Feng Fu, who's now at Dartmouth, is the first author of, on the evolution of homophily. The gist of the insight about homophily is the following. Why would we evolve to be homophilous? I mean, most of the accounts of homophily to date are what I would think of as tautological. They say, well, people are homophilous because they're more comfortable in the presence of people they resemble. And why do they prefer the company of people they resemble? Because they're more comfortable with, you know, it's a kind of circular reasoning. But why would we evolve this preferential interest in the people we resemble? And one idea is that it's a social heuristic. In other words, if you're trying to design, where should I live? You know, where can I find food that is suitable to my body? Or temperature conditions that are suitable to me, or who I want to hang out with someone who lights a fire when they're cold, because I'm also cold when they feel cold. As compared to me, I don't need to be with someone who's lighting a fire when they're cold because I don't feel cold. You know, my wife and I have been arguing about the temperature for 20 years, like every other couple I know. And you know, she'd be better off, I think, with a woman, I think, who, you know, had a similar temperature, thing. Actually, you know, heterosexuality is the one big exception, by the way, to homophily. Anyway, although there's a very interesting literature on the origins of homosexuality as well, which we can talk about. But anyway, so the idea is that by hanging out near people you resemble, they are like probes for a safe environment for you. Or they generate positive externalities, like they go finding food that they like, and there's too much of it where they find it, and there's some for you. So by tagging along behind them, they have created this positive spillover. So this is one idea about the origins of homophily, which I think is quite plausible. It's very difficult to test these ideas, of course. But anyway, I hope I'm partially answering your question. Am I answering it? I've lost track now. Yeah.
Yeah, thank you.
All right, thank you all very much. I'll be back in 23 minutes and meeting with whoever wants to meet with me. And thank you again so much for having me. I wish I were there in person and I could go out and have a meal and actually have a glass of wine with you, but it will have to do it by the internet.
Right. Thanks, Dr. Christakis.